Hello students, it's Mr. Naren, your one and only chemistry teacher. In this video, I'm going to go over the entire Lewis bonding practice worksheet. So if you're watching this, you can pause it, you can do what you want, but I hope you're following along with me. And if you're watching this video and you haven't tried to do it on your own yet, you need to go do it on your own first. This is meant for you to check your work with, okay, so that you try it on your own. If you just copy along with me, you're not going to learn it as well. So let's go ahead and get right into it. All right, so here we go. These are the problems that we started yesterday in class. So they should look familiar to you. We did these. Let's take a look at this one right here, okay? I don't think I've gone over it yet. So we got silicon 2, or Si2Br6. So I'm not making you do the structure for this one. I just want you to be able to name it. And so if I look at this, I see that 2 right there, and I say, oh, well, 2. I look at my prefixes, okay? We got a polyatomic ion sheet here. This is in your general folder. The prefix for 2 is di. So we'll do disilicon, okay? That's where that di comes from. And then we have Br with a 6. So once again, I look on my covalent naming prefixes, and I see hexa. So this is going to be hexabromide. Now, I add the IDE ending because it's the second element. You always add that to the second one, all right? So this is what we got. Another thing that I want to remind you guys for, because we're going to learn other naming practices soon, you only use prefixes when you're dealing with 2 nonmetals, okay? And all of these on this worksheet are nonmetals, so we're good. Let's take a look at the next one. That's all there is to that. Let's look at the next one. SCl4. So in this problem right here, if I have an S, that tells me, oh, well, it's just sulfur. And notice, if there's nothing written as a subscript underneath that S, so it just says S with a blank, that really means there's a 1 there. We didn't write it, but that means there's a 1 there. So this one is literally just going to be sulfur. Okay? Don't put a mono in front of it. We typically don't do a mono if it's the first element, so it'll just be sulfur. And then we have a 4. Okay, we have that 4 right there. Look at my prefixes. It's tetra. So this is going to be tetrachlor, not ene, chloride. So sulfur, sulfur, tetra, and then we add an IDE because it's the last, it's the second element. All right, let's go ahead and do our bonding. First step, our Lewis structure. Our first step is to count up our number of valence electrons. I see that sulfur is in group 16, so it's going to bring 6 valence electrons to the table. Chlorine is in group 17, so it's going to bring 7 valence electrons. And because there are 4 of them, I'm going to multiply by 4. So we do, let's see, 7 times 4 is 28, I think. Yeah, plus 6 is going to be 34. So we got 34 valence electrons to work with in this problem. Now, next thing I need to do, I got to figure out what is going to be the central atom. Is it going to be sulfur or is it going to be one of these chlorines? And what we do to find that out is we have to find the least electronegative. So here's sulfur with an electronegativity of 2.58, and here's chlorine with 3.16. Basically, a good rule of thumb is, because fluorine is the most electronegative, whichever element is furthest away from fluorine is going to be least, and the least electronegative is what becomes our central atom. So I'll go ahead and put S in the middle, and I need some chlorines all around, like so. All right. And so at this point, if I were to stop right here, look how many electrons we just dealt to the problem. 2, 4, 6, 8. Each of those single bonds has 2. Okay, I'm going to make those go away. I don't like doing that. I think it looks sloppy. But if it helps you, by all means, do it. So we just used up 8, so we don't have 34 electrons anymore. Now we have 26 valence electrons to use, all right? And how am I going to distribute them? I'm going to distribute them to the outside atoms first, so all these chlorines. So, and I do it in 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now, you may not like that because you're going to look at that and say, well, Mr. Darren, we just used 24. We still have 2 valence electrons left. And you're correct. We do have 2 valence electrons left. But look, each of these chlorines is full. It has 8 out of 8. And you can check that with all of them. Each of the chlorines has 8 out of 8. Sulfur has 8. But if you guys remember, I told you, sulfur is one of those elements that has an expanded octet. It has an expanded octet, which means that those extra 2 can actually go right there on sulfur. It's happy having 10. It can have 10 electrons, okay? And so we can check that. Let's check to make sure everything's happy. Or actually, I'm going to count them up first to make sure I did that right. 2, 4. Always check. Remember, we had 34 valence electrons to start with, so I'm just going to make sure I got them all. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. Yep, everything's accounted for. Another thing that you can look for when you do this is make sure that each of your elements that's supposed to have 8 has 8, and each of your elements supposed to have a different amount has a different amount. So I can go through and I can say, yep, each chlorine has 8 out of 8, sulfur has 10, and that is okay because it has an expanded octet. Let's take a look at the next one. And by the way, if you're trying to remember what the expanded octet is, there's actually a section on the periodic table that you can look. Okay, phosphorus, sulfur, chlorine, arsenic, selenium, bromine, krypton, and then iodine and xenon are the elements that are special, and they get more than 8. Let's take a look at CH4. This is a little bit easier. It's much easier. So that C, notice there's nothing written underneath that C, so that means it's just going to be carbon. It doesn't get a mono prefix. It doesn't get any prefixes, okay? The next one, we have a 4 right there, so that means that's going to be tetra. Okay, we have a tetra because we have that 4 right there. And it's not going to be tetrahydrogen, it's going to be tetrahydride. Okay, tetrahydride, just like that, carbon tetrahydride. Okay, let's add up our valence electrons. That's it for the naming. I mean, there's not much to it. Use your prefixes, use your common sense. Carbon, it's in group 14. It's going to get 4 valence electrons. Hydrogen is in group 1. So it gets 1 valence electron, but there are 4 of them. So we'll multiply it by 4. We get 8 valence electrons to deal with. Okay, that's it. That's all we're doing over there. And so now that we have 8 valence electrons, I know, without even looking at electronegativity, that carbon's going to go in the middle. And the reason I know that, as I told you, write it down twice in the notes yesterday, hydrogen can never be in the central atom, okay? And so, I've got to do carbon, got my 4 hydrogens, and for those of you that are paying attention, I just did 4 single bonds at 2 electrons each. I just used up every electron I had just making that. And that is okay. Because take a look. Carbon, my central atom, has 8 out of 8. It's good. It has an octet. That's what it wants. And each hydrogen has 2 out of 2. Hydrogen only needs 2. It's called a duet. And each of my hydrogens is satisfied. And so that is all there is to CH4. Everybody's happy. Everybody has what it needs. Let's take a look at our next one. B2SI. Okay, B2SI. That 2 right there, right off the bat, I know that means that I am going to have a prefix on boron. So this one is going to be diboron. And then I have Si. This is one of the ones that sounds kind of silly. We can put a mono in front of that. That's fine. Because there's just a 1. We know there's a 1, even though it's not written, okay? We know there's a 1 there. We don't have to have it written. So this is going to be monosilicide. Okay? So we have diboron monosilicide. Now let's figure out what's going to be in the middle. Is it going to be boron? Is it going to be silicon? Let's take a look at our electronegativity. Boron is over here, okay, with 2.04, and silicon just barely has lower negativity, electronegativity. And so silicon has less electronegativity. Silicon is what it's going to be. So Si goes in the middle. Okay, like so. We got 2 borons flanking it, B and B. And now we got to count up all of our valence electrons. I should have done that first. I apologize. I just get excited. I like to draw the structure. Boron is in group 13, so that means there's going to be 3 valence electrons. Because there are 2 of them, we'll multiply that by 2. Silicon is in group number 14, so it's going to bring 4 valence electrons. When we add all this junk together, we get 10 valence electrons. Okay, 10. Let's start spreading them out. Now, one thing I'd like to remind you guys about, in fact, if you don't believe me, check your notes, boron is special. Boron does not need to have 8 valence electrons. It is happy only having 6. It gets a sextet. Okay, so boron is special. It needs a sextet. It only needs 6 out of 6, not 8 out of 8. All right, so that's something we need to be looking for. But anyway, I'll go ahead and spread out the 10 valence electrons first. 2, 4, 6, 8, and I could stop right there and borons would be happy. So 10, the final 2, are going to go on the central atom. Let me clean that up a little bit. I like my, when I'm doing just 2 pairs on the outside, I like to put them kind of at an angle, like so. Because they're electrons, they are repelling one another. This way, the electrons can all spread out and be nice and even. So that's what it should look like. Let's double check. Boron has 6 out of 6. It's good to go. This boron over here, it's 6 out of 6. It's good to go. And then silicon, it is not good to go. Because if we take a look at this, silicon is going to have 6 out of 8, and it is not satisfied yet. So all we're going to do to fix this, it's not a big deal. And I don't really care which one you pick. You learn more about this in AP. But basically, one of the borons, I'll just pick the one on the right, is going to have to donate its electrons and form a double bond. Not both of them, just one side. Because if I did both of them, then silicon would have more than 8. Okay? But if I donate them from that side, now it doesn't have those electrons anymore. It becomes another bond. So we have a double bond over on the right side. Hopefully one note will catch up to me here in a second, because it should. There we go. So it has a double bond on that side. I'll move those electrons where they should be, just like this. And now everything's happy. And so the fact is, if you were in AP chemistry, you would learn this is called resonance. So basically what that means is we have a double bond, but it could either be on that side or it could be on this side. It could be either side. It just kind of switches back and forth. But that is good enough for me. That right there is good enough for me. Let's look at the next one, NF3. NF3. Let's name it first. Because nothing is written right there, we know that means 1. I'm just going to write nitrogen. I am not going to write mononitrogen. I don't write mono if it's the first one. Then we have F with a 3. I know the prefix for 3 is tri, just like a tricycle. Okay? And so we have tri, fluor, not ene, ide, because it's my second element. So we have nitrogen trifluoride. All right? Let's go ahead and get this started. Let's do our valence electrons. Nitrogen is in group number 15, so it gets 5 valence electrons. Fluorine is in group 17, so it gets 7 valence electrons, and there are 3 of them. Okay, so we're going to add them together, 26. 26 valence electrons is what we have to deal with. Now, which one's going to be the central atom? The least electronegative? I'll give you a hint. It's not fluorine. Fluorine is the most electronegative element on the periodic table. So N is going to go in the middle. So we'll put N in the middle. F, F, F. Like so. And now we've got to distribute some electrons. At this point, we just used up 6 electrons, making those single bonds. So now we have 20 valence electrons left to deal with. And so I'm going to distribute them on all my fluorines. Let me center that a little bit better. I can do better than that. There we go. All right, so here we go. 2, 4, 6, 8, 10, 12, 14, 16, 18. Well, Mr. Nairn, now all the fluorines are good, and we still got 2 left over. Yeah, I wonder where they're going to go. Because if we stop and look at where we are right now, we got 2 electrons left to use, but every fluorine is happy. I mean, I'll just pick one. They're all the same. But this one has 8 out of 8. It's good. And each fluorine is good, but nitrogen is not happy. So where are those extra electrons going to go? They're going to go directly onto nitrogen. So you get an unshared pair that's on nitrogen. And that's what you end up getting. That's it. We used up our last 2 electrons. We're good. All right, let's scroll down. Did that in class. We did these sort of in class. So students, if you're watching this, I decided to go ahead and omit these two. Chlorine dioxide is good practice, but technically that should be chlorine dioxide with a -1 charge, and I kind of messed that up. Let's not bother with that. If we were in person in class, we would take the time. Let's not play that game right now. Hexaboron silicide. Hexa gives me the 6, so it's going to be B6. Silicide just means 1, so it just becomes Si. That's what we have over there. Then we have chlorine dioxide, so that's Cl. Notice there's no prefix. That tells me that it means there's just one chlorine, so we just get Cl with no subscript. And then dioxide means 2 oxygens, and that's what I've written over there. Let's take a look at hydrogen iodide. This is a very friendly covalent molecule, and for reasons that'll make sense in a moment. Hydrogen iodide, how many hydrogens? Well, if nothing is written, that just means 1. Okay, if nothing's written, that just means 1. And for iodide, you could make this hydrogen monoiodide, but the result's still going to be the same. If nothing's written, that just means a prefix of 1. So, H with a 1 that we don't write, capital I with a 1 we don't write. It's just hi, that's it. Let's add up some valence electrons. Hydrogen has 1 valence electron. Iodine is in group 17. It has 7 valence electrons. Okay? So we have 8 valence electrons total to deal with. The central atom is going to be iodine. How do I know that? Because it's not hydrogen. Hydrogen can't be the central atom. And so iodine is going to be central. Not that it matters much for this problem. So in my one single bond that I've drawn, 2 electrons just got used. I got 6 valence electrons left. And hey, iodine sure would love to have a total of 8 valence electrons. So if I put all 6 of them on iodine, look at what we got. Iodine is happy. It has 8 out of 8. And hydrogen is happy. It has 2 out of 2. Remember, hydrogen only needs 2. It's not a very big atom. 2 out of 2 is more than enough. It gets a duet instead of an octet. So there you go, HI. Let's look at iodine pentafluoride. It's a little more interesting. Iodine, once again, if they don't write anything in front, that tells us that there's just one iodine. Okay, just one iodine. So I'll go over here and write a capital I with nothing underneath it. Remember, we don't write the ones. And then I have pentafluoride. That prefix penta, okay, like pentagon, means 5. So I'm going to go over here and put an F, and I'm going to put a subscript of 5 to represent 5 fluorides bonded to this iodine. Okay, let's go ahead and do our Lewis structure. Okay, we're in the home stretch. We're almost done with this. Okay, so I need to check, or I need to look. Iodine is, sorry, I got a text in the middle of me talking. It messed me up. So 17, iodine is in group 17. It gets 7 valence electrons. And then we have fluorine, which also has 7 valence electrons, but there are 5 of them. So we're really doing 7 times 6, which I can definitely do, not with the calculator. I definitely didn't go over there and do a calculator because I don't remember multiplication tables. So I got 42. So we got 42 valence electrons to divvy out and figure out where they go. Not a big deal. Not a big deal. Okay. Wait, why did I write 4? I meant to write 42. Let's fix that. There we go. All right, iodine or fluorine, which is going to be the central? Well, if I've told you once, I've told you 1,000 times. Central atom is going to be the least electronegative. And because fluorine is the most electronegative, it's going to be iodine. So we got an I in the middle. And then I'll put my 5 fluorines around it, like so. It's a good thing iodine goes in the middle, because if I were to stop right now, look at just iodine. Iodine has 10 valence electrons, and that's okay. Iodine is one of the exceptions that has an expanded octet. Check your notes. Iodine's on that list. It can have more than 8. And so we've just used up 10 of our valence electrons. Now we got 32 left to deal with. So let's see how it's going to turn out. Hopefully well, because I didn't practice this one earlier, and I don't remember. So 32, I'm going to spread it to all those fluorines. Okay, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. And so if I've done 30, I can stop because I can see that all my fluorines are happy, but we still have 2 valence electrons left to deal with. And so if all my fluorines have 8 out of 8, that's all they can hold, iodine is going to have to take the extra ones. And we'll put those extra 2 right there on iodine, okay, which is fine. Iodine can have more than 8. It already did. So that's all. That's all for that one. Let's take a look at the next one. For this one, we're not going to do our Lewis structure. Dinitrogen trioxide. So di tells me 2. How many nitrogens? 2. So it's going to be N2. And then trioxide, that prefix tri tells me 3. How many oxygens? 3. N2O3. And we're not going to bother doing the Lewis structure for this one. Let's take a look at the next one. Phosphorus triiodide. How many phosphorus? Well, if they don't give us a prefix, okay, that tells me I just have 1 phosphorus. So I'll go over here and just do a P. I'm not going to write a 1 underneath it. Now, tri, T-R-I, means 3. So how many iodine, or how many I's? It's going to be 3. Just like that. Okay, so there's that. Now we got to do our Lewis structure. Same as before. And I know you guys are tired of doing it, but this is good practice. Repetition helps with things like this. Phosphorus is in group 15, so it's going to get 5 valence electrons. Iodine is in group 17, so it gets 7 valence electrons, and there are 3 of them. We add all this up, we get 26 valence electrons to deal with. All right, which one's going to be my central atom? I hope it's phosphorus, but let's double check. Phosphorus has an electronegativity of 2.19. Iodine is 2.66. So phosphorus is less electronegative. Phosphorus is going to go in the middle. So I'll put P in the middle. Spread it out like so. Already, I just used up 6 electrons. If you don't believe me, look at those single bonds. They're 2 electrons each. So now we have 20 valence electrons left to deal with. And just as before, I'm going to spread them all out on each of these iodines. So 2, 4, 6, 8, 10, 12, 14, 16, 18, okay? And so once again, if I were to stop right there, all my iodines would be happy. It has 8 out of 8 on each of them, okay? All of them have 8 out of 8. We're good. But my phosphorus is not happy. Luckily, I still have 2 electrons left. If you don't believe me, you can count them up. I still got 2 valence electrons left, and so they're going to go on phosphorus, just like that. And that's all there is to it, guys. So that's what I've got to tell you about doing these Lewis structures and your covalent naming. Remember, covalent is with 2 nonmetals. When you're doing covalent, that is the only time you use prefixes, is between a nonmetal and another nonmetal. We'll talk to you guys more soon. Thank you for watching.